Hello again. Get ready, folks. This is where things get very, very calculus-y. This is the most calculus that we are going to get in this unit. We are going to actually talk about the derivative function and how to find it for specific functions. This is lesson 12.3, so let's get started. By definition, every point on a smooth graph has a line that can be drawn tangent to it. So you can see I've got that blue curve, it's very smooth, and I've got a red point on there, and I've drawn a tangent line to the curve. So you can see that the slope of the tangent line kind of matches the slope of the curve at that one point. It's kind of like putting a flat board on a roller coaster track, if you can see it from the side. So how would that board lay on that roller coaster track? That's one way of looking at it. What the derivative function does is it takes any x of the point that you're on, or it takes the x of any point that you might be on, and it calculates the slope or the gradient of that tangent line. Very, very cool stuff. It can tell you exactly how steep the curve is just by you inputting the x value of that point. So the notation we have to get used to is dy by dx. It looks like a fraction. It's not exactly a fraction, doesn't really behave exactly like one. It's just a notation. Or we can use f prime of x. F prime of x is a different function from f of x, and it is the derivative function based on what f of x was. So we're going to be looking first of all at y equals x squared. That's where we spent the majority of our time in the last lesson. But instead of looking at a specific x value, I'm just going to look at a generic x value that I'm going to call x. And I'm going to look at an x value that's a little bit bigger than that, so I'm calling that x plus h. And if I do that, to get the y values, what I'm going to do, because it's y equals x squared, I'm going to square each of those x values, and that becomes my y's. So on top I have x plus h squared minus x squared. I've subtracted my y's. On the bottom I have to subtract my x's. So that's just x plus h minus x. If I expand the top, I have to expand that binomial properly. It's being squared, so I can't just square each term. That's a big no-no, so I have to actually FOIL it out or remember Pascal's triangle or something to get x squared plus 2xh plus h squared, and then I have to remember to subtract the x squared that's still up there. On the bottom you see x plus h minus x. Well, those x's, one's positive, one's negative, they will subtract out and leave me with just h on the bottom. If I look at the top again, I see that the x squared at the very beginning and the minus x squared at the very end will subtract out, leaving me with just the two terms that are in the middle, the 2xh plus h squared. And then on the bottom I still have h. What I notice now is that every single term in the fraction has an h in it. So I can divide top and bottom by h. And if I do that, I get 2x plus h all over 1, or just 2x plus h. Now remember what I'm doing with that h. I'm letting that h approach 0, because eventually I want there to be no distance at all between x and x plus h, meaning that h would have to equal or approach 0. And if I do that, this function will become 2x. So the derivative of y equals x squared is 2x. What that means is, wherever you are on the graph of y equals x squared, if you tell me what the x coordinate is, the slope of the tangent line is going to be double that. Okay, so now let's step it up and we'll talk about y equals x to the third. We're going to do exactly the same thing. This is how we always find derivative functions, is we find the slope between x and x plus h, and we let h approach 0. Okay, so I now have to cube my x's to get my y's. So that's why the top is x plus h cubed minus x cubed, and the bottom is just x plus h minus x. Okay, expanding that cubic, or that binomial being cubed, expanding that properly, I get x cubed plus 3x squared h plus 3xh squared plus h cubed, and then I've got that minus x cubed that was already up there. All of that goes over h, because remember the x's subtract out on the bottom. The x cubed at the beginning of the top and the minus x cubed at the end of the top, they will subtract out, and all I will be left with is the three terms in the middle, the 3x squared h plus the 3xh squared plus the h cubed. All of that is over h, and once again, every single term has at least an h in it, so I can divide top and bottom by h. And I'm left with 3x squared plus 3xh plus h squared all over 1. And I can ignore the over 1 part. Okay, now as h approaches 0, the first term stays there, it's got no h's in it, but the 3xh is going to go to 0, and the h squared is going to go to 0, so all I will have left is 3x squared. What that means is the derivative of y equals x cubed is 3x squared. So if I have any x on that graph and I want to know the slope of the tangent line, I just square it and multiply by 3. Now let's look at y equals x to the fourth. To calculate the slope, we're going to do x to x plus h again. Now I'm raising my x's to the fourth in order to get the y's. So I've got x plus h to the fourth minus x to the fourth on top. And on the bottom, I've just got my x's being subtracted just like normal, x plus h minus x. So if I expand that binomial raised to the fourth, I've got x to the fourth plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the fourth, and then I've got to subtract that x to the fourth that was already sitting up there. On the bottom, the x plus h minus x is just h, just like it was in the other examples. Well, again, I've got x to the fourth minus x to the fourth on top, so I'm left with the 4 middle terms all over h. And once again, every term now has an h in it, so I can divide top and bottom by h, and I'm left with 4x cubed plus 6x squared h plus 4xh squared plus h cubed. And remember, I'm letting h go to 0, so any term that's got an h in it is going to go to 0. That leaves me with only the first term, that 4x cubed. So what that means is the derivative of y equals x to the fourth is 4x cubed. So if I have any x, if I have any point on this curve and I want to know the slope of the tangent line, I take the x coordinate, I cube it, and I multiply it by 4. That will get me the slope of the tangent line. So let's see if we can see a pattern from what we've done so far. When we did x squared, we got a derivative function of 2x. When we did x cubed, we got a derivative function of 3x squared. When we did x to the fourth, we got a derivative function of 4x cubed. And just for, I'm going to give you this one, if we were to do y equals x to the fifth, we would have gotten a derivative of 5x to the fourth. So hopefully we can see a pattern. What you should notice is that the exponent of f of x becomes a coefficient in f prime of x. So I kind of move that down to the front and make it a big number. The exponent in the derivative is actually one less than it was in the original function. So those two things always happen in every single case. So if I wanted the derivative of x to the n, I would move that n down front and I would subtract 1 from it to get my new exponent. So the derivative of y equals x to the n is n times x to the n minus 1. That's the general rule that you can use. All right. So here's some more examples that still fall into that pattern. It applies to negative exponents as well. So the derivative of x to the negative 1 would be negative 1 times x to the negative 2. Following that same rule. I can use it on fractional exponents. The derivative of x to the 1/3 would be 1/3 times x to the negative 2/3. You always have to subtract 1 from that old exponent to get the new one, no matter how weird the exponent is. Furthermore, if I had the derivative of a constant, I would get 0. So the derivative of y equals k is 0. And then the derivative of just the function x is 1. So those are some rules that will help you find derivatives, especially later on when we're going to do some operations with these derivatives. But for now, if you have any questions, please let me know, and I will see you tomorrow.